Hello everyone, thank you so much for attending my presentation. I'm Yemo from North Carolina State University. Today I'm going to present our work. What time is it? Student modeling needs to know. Here is the outline for my talk. I will start with background. Modeling student cognitive processes is highly complex since it is influenced by many factors such as motivation, aptitude, and learning habits. This is especially challenging for computer-based learning environments because of the high volume of features and tools. Recently, deep learning models such as long short-term memory and classic Markov models such as Bayesian knowledge tracing have been successfully applied to predict student performance in the future based on their historical data. However, both LSTM and BKT are designed to handle sequences of events with discrete timestamps, not considering the continuous aspect of time. Ever since the mid-1950s, student response time has been used as a preferred educational assessment to evaluate how active and accessible student knowledge is in cognitive psychology. For example, it has been shown that response time reviews student proficiency and negatively correlated with their performance. Also, Response time has been suggested as an indicator of student engagement in answering questions, as well as an important factor for predicting motivation in learning environments. Therefore, by not taking the time intervals into consideration, the design of traditional LSTM and BKT may lead to suboptimal performance for modeling student learning. And here, our research question is, by taking time awareness into consideration, would time-aware LSTM outperform other traditional student modeling methods on both self-paced and tutor-driven learning environments? Next, I will introduce the methods in this work. First, long short-term memory. LSTM is a special type of recurrent neural network which is designed to avoid the long-term dependency problem. The interval structure of each LSTM module is shown here. There are three major components. Forget gate determines the information to keep or remember. Input gate determines what information is new and requires updating. Output gate decides what values from the cell state to add it to the hidden state output. They interact with each other to control how information flows. A standard LSTM assumes that the elapsed times between elements of a sequence are uniformly distributed, which is not always true in the educational domain. Thus, in this work, we apply time-aware LSTM, which is proposed to handle the temporal dynamics of sequential data with time irregularities. The T-LSTM architecture is shown here. Apart from three gates in standard LSTM, it also contains time decay component, which mainly plays a role to adjust the short-term memory. If the gap between two steps is significantly huge, like few hours in our domain, it means there has been a long time with no student-tutor interaction. Thus, there is not much point to heavily rely on the previous short-term memory to predict the current output. And here, we apply gt equals to 1 divided by log of e plus t to transform the time duration into an appropriate weight. In this work, we investigate the effectiveness of TLSTM via the early prediction of both student success and learning gains. As far as we know, no prior studies have explored TLSTM on both computer-based programming systems and intelligent tutoring systems. The third one is recent temporal pattern mining, or RTP, which was originally proposed to find predictive patterns from complex multivariate time series data. Generally speaking, our RTP mining is conducted by the following four steps. First, we convert binary time series data into state interval sequences with the form of feature, value, start time, and end time. Then, we extract frequent recent temporal patterns from those state interval sequences by considering two temporal relations, before and co-occur. and run RTB mining for different classes of data separately. Then, with those discovered patterns, we transform each student trajectory into an RTB binary feature matrix. Finally, we apply logistic regression classifier on the matrix to predict the outcomes. Last one, Bayesian knowledge tracing. BKT is one of the most widely investigated student modeling approaches. The model itself is rather simple. As we can see from its network topology, it is a two-state hidden Markov model. The shaded node S represents the hidden knowledge state, and the unshaded node O represents the observation. In order to apply BKT to our dataset, we captured and mapped all students' actions based on the learning opportunities of knowledge components step by step. Next, I will talk about experiments. In this work, we explored different student modeling tasks based on the characteristics of two different learning environments. One was the task of early prediction of student success in an open-ended, self-paced programming environment called iSnap, while the other is the task of early prediction of student learning gains within a tutor-paced probability tutor called Pyrenees. First, iSnap. iSnap is an open-ended, block-based programming environment where students are self-paced to complete an assignment. And in this work, we focus on one homework exercise named Squirrel, where students are asked to write a procedure that draws a squirrel-like spiral, as shown in the figure. Correct solutions usually take 7 to 10 lines of code. We applied the binary feature state representation for student code trace data, which tells the presence or absence of specific features. For example, the feature state 1000001 shows that feature 1 and 7 are present, while the other 5 features are not. Overall, we collected 171 student code traces from 4 semesters, making a total of 31,064 tagged snapshots. And in this work, we classify the students who finish the programming assignment in 1 hour or less and got full credit as successful, labeled with 0. Those who either failed to complete or submit the assignment within 1 hour as unsuccessful, labeled with 1. Based on this definition, 59 of 171 students are in the successful group. The remaining 112 students are in the unsuccessful group. To predict student success, we are given the first up to n minutes of the student sequence data, and our goal is to predict whether the student will successfully complete the programming assignment at any given point in the remainder of the sequence. In this task, we have 4 models involved: logistic regression, RTP, LSTM, and TSTM. Since LR does not handle sequence data directly, we applied a loss value approach to treat the loss measurement of each attribute within the given observation window as the input to train models. For RTP, as mentioned earlier, we applied LR on the transformed RTP binary matrix to predict student success, while both LSTM and TSTM are applied with one hidden layer of 128 neurons. Please note here we does not include BKT because for the open-ended domain like iSnap, there's no predefined knowledge component or steps that students must achieve to solve the problem. Thus, it's hard to map student actions in iSnap to learning opportunities defined in BKT. The second environment is Pyrenees, which is a web-based ITS teaching probability. Different from iSnap, Pyrenees is a traditional ITS that the tutor guides students through solving each problem and dominate the process. Pyrenees covers 10 major knowledge components such as addition theorem, the complement theorem, and so on. The figure here shows the interface of Pyrenees. Students need to take 10 pre-test questions, 12 training problems, and 20 post-test questions. And in this work, we only take the student trajectories from the training phase to train our models. And we collect the data from 6 semesters. In total, we have 102,948 data points from 1190 students. How do we evaluate students' learning gains on parents? Here, we used a qualitative measurement called quantized learning gain, QLG, to determine whether a student has benefited from our learning environment. To infer QLG, students are split into low, medium, and high based on their scores in pre-test and post-test respectively. As indicated in the graph, solid lines represent the high QLG group, labeled with 0. A student is a high QLG if he or she moved from a lower performance group from pre-test to a higher performance group in post-test, or remained in high performance groups. The other dashed lines are in low QLG group, labeled with 1. As a result, we have 487 of 1190 students in the high learning gain group, and the remaining 703 students in the low learning gain group. And in the learning gains prediction, we have 4 models. Same with the success prediction. We have LR, LSTM, and TLSTM. Here we have BKT instead of RTP because in Pyrenees, students' response are determined not only by their underlying knowledge state, but also by the pre-designed turn-taking nature of the system, which could obscure the temporal patterns found by RTP. And for BKT, we first trained different models for each case respectively and then extracted them as features for logistical regression to make the final predictions. In Pyrenees, students usually take around 2 to 4 hours to complete the whole process. Thus, we are given the first up to n% of a student sequence data to predict student QLG. Let's look at the results. This table shows the success prediction results on the open-ended student self-paced programming iSnap tutor. We evaluated all the models on different metrics including accuracy, precision, recall, F1 measure, and AUC score. At first 6 minutes, we can observe that TLSTM in the last row outperforms all the other models, and it generates the highest score on every measurement except that the best recall comes from RTP. For the overall AUC, TLSTM is still the best. Here, we have the results of QLG prediction on the traditional tutor scaffolded probability ITS Pyrenees. For the first 30% sequence result, TLSTM generates the best performance on every measurement except that the best recall is from LR and the best F1 is from LSTM. And both LSTM and TLSTM outperform BKT across all the metrics. For the overall AUC, LSTM and TLSTM have very similar performance and are equally good. Still, they achieve higher mean AUC scores than BKT with a lower standard deviation. With these results, we can go to the final conclusion part. In this work, we investigated the effectiveness of a time-aware model, TLSTM, on the 2 different prediction tasks. Our results show that TLSTM consistently outperforms the other models such as LSTM, RTP, and LR on the task of predicting student success on iSnap at all observation windows from first 2 minutes to 20 minutes. It suggests that TLSTM can better learn the difference between the 2 groups with the help of time awareness in the open-ended programming environment. On the other hand, for the task of predicting student learning gains in Pyrenees, TLSTM outperforms LSTM and BKT on the early stage with only 30% of the student sequences, but afterwards, time awareness does not help much when more data is available. That's it. Thank you.